Okay, so welcome to this lecture on the peer-to-peer network. And we will now remove the last sensor in the system, which is the shared folder. And we will replace that with a network of computers, a network of Bitcoin full nodes, or actually cookie token full nodes, but yeah. Okay, suppose that Rashid here creates a block and wants to put it in the shared folder. And for some reason, one reason or the other, the admin of this shared folders, you know, there's always an admin in a centralized system. There's always an admin. And with this shared folder, it's the shared folder admin. And this admin doesn't like Rashid's block for some reason. It might be because there's a controversial transaction in there. Maybe it's a donation for a political organization or anything. I don't know. But the admin won't allow this block to happen. So admin can block this block from entering the shared folder. And this is a very big problem. And it's also the last piece. This is also the last way to censor data in this system. And we're going to get rid of this problem with something called a peer-to-peer network. A peer-to-peer network is a network of computers that are interconnected. Each node in this network doesn't have to be connected to every other node, but each node needs to be connected to some nodes, at least one. But so let's have a quick look at how this would work. Suppose now that Rashid finds a block. His node here finds a block, and he publishes this block to all nodes that he's connected to. So he sends it to Xi, he sends it to Tom, and he sends it to the cafe's node. And the cafe's node will, for example, the cafe's node will verify the block to see that it's correct. And if it is correct, the cafe will propagate the block further to his neighbors, like Lisa, for example. So in this way, blocks will propagate the network from its origin, Rashid. And this makes it harder to censor blocks. Suppose that the cafe turns evil and wants to prevent Lisa from getting this block. So Rashid pushes out the block to the cafe and Tom and Xi. And the cafe refuses to send the block to Lisa. That's not very effective because Lisa will probably get the block from Tom or Xi instead. So in order to prevent Lisa from seeing this block, the cafe and Xi and Tom would all have to agree to censor blocks for Lisa. So it's much harder now to prevent information from propagating in the network. And also, since we have this nice peer-to-peer network, we don't only use it for propagating blocks. We also use it for propagating transactions that are waiting to be confirmed in blocks. So if Alice wants to pay to Bob over here, Alice is connected to one or more nodes. This might be a lightweight wallet. It could be a full node as well, but it's connected to one or more nodes. That's the point here. And they simply send their transaction to the full nodes that they are connected to, and they will verify this transaction. And if it's valid, it will be sent further to their neighbors and so on. And it will propagate the full network. And eventually, at some point, some node that Bob is connected to will also receive this transaction. And this node will then send that transaction out to Bob as well. And Bob will be able to see that he's about to receive 1 Bitcoin. So he sees that there is a pending transaction going on. But it's not confirmed yet. So Bob cannot trust this transaction yet. It's not confirmed in a block. Okay. So let's have a look at how the communication between two peers happen. So Tom and Lisa, for example. So we have Tom and Lisa, and the communication happens over TCP, Transmission Control Protocol, which is a standard way of communicating. So Tom will contact Lisa's IP number and connect to port 8883, which is the default port for Bitcoin. So he kind of asks Lisa's operating system to open a connection to Lisa's program that's running on port 83333. And the operating system will reply back with sure, welcome, which is a syn ACK, and Tom's computer will send an ACK back, acknowledge back to Lisa. And then they have established a communication channel. Now Tom's node software and Lisa's node software, which is Lisa's computer program, will now be able to talk to each other over this channel. But that's not enough. You need a common language. I mean, if Tom says buenas noches to Lisa, Lisa might not understand it because she doesn't understand Spanish. So they need a way to communicate. And we do that with messages, a protocol, a messaging protocol that's used in Bitcoin. And an example of such a message is an inv message, which stands for inventory. It means that Tom informs Lisa about stuff that he has. He has to offer this stuff to Lisa. So Tom has just received a transaction from somewhere and a block and another transaction and wants to inform Lisa that he has these items. He has this transaction, he has this block, and he has this transaction. And he refers to them by their transaction IDs and their block IDs, like this. And Lisa receives this message and can decide to fetch those items from Tom if she needs them. So this is a way to tell someone else what they have. So let's follow a transaction through the peer-to-peer network. Let's start from the very beginning, where a wallet sends a transaction to a node in the network. So John sends a transaction to Tom's wallet, to Tom's full node, sorry. And let's see what messages are exchanged. So first of all, since this wallet is the creator of the transaction, this wallet will automatically have this transaction, of course, and he wants to propagate the transaction. So he sends an inv message to Tom so that Tom is informed about the existence of a transaction with this certain transaction ID. And Tom checks his data to see if he has the transaction already, which he doesn't. So he will need to request the transaction from John's wallet. So he sends a get data message with a transaction ID. And then John's wallet will reply with the transaction. It's a transaction message, TX message. And I want to say also that these messages are a simplification of the messages. There are more stuff in these messages, but this should give you an idea. This is the vital parts of these messages, so to speak. There are some, information about what network the message belongs to, and so on. Because there are test networks and different kinds of Bitcoin networks, and there's a main network. So you have different network identifiers for different networks. Okay, so Tom has now received this transaction from the wallet and wants to propagate it further to Lisa and Xi and Rashid. And it goes the same way. Tom will send an env to Xi, and Xi will get the ask for the data, and Tom will send the transaction. And also, Lisa, let's go back here. Since Lisa received this transaction, she will inform her neighbors about the existence of this transaction. So Lisa will send an env message to Xi like this, but she already has got the transaction itself. So she can verify that, okay, I already have this transaction, so I don't have to ask for it. And this is why you don't always just send a transaction as is, because that would waste a lot of bandwidth. So now she doesn't have to fetch this data from Lisa. And so this is how the transaction would propagate the full network, and somewhere the cafe will receive this transaction and wants to inform its lightweight wallet about it. So this is a nice setup where the lightweight wallet is connected. This is the cafe's lightweight wallet, and it's connected to its own full node here. So this lightweight wallet knows that if my full node receives a transaction that I'm interested in, I will get it. So the cafe will send this, the cafe's full node will send it to their lightweight wallet. And it happens in the exact same way as before, an in followed by a get data and a transaction. And the lightweight wallet will now be able to show to the user, to the clerk, that you're about to receive 10 cookie tokens, which is great. So now it's just a matter of waiting for the cafe. Now it knows that there is a pending transaction aimed for them, but it's not confirmed yet. But it's a good way to show to the user that something is actually happening. There is a transaction now, but it's still pending. And now suppose that this transaction also reaches miners, all the miners, hopefully, in the peer-to-peer network, so that any miner who wants to include John's transaction, suppose that he pays a decent fee so that the miners are willing to take it into their block. So Rashid is making a block with John's transaction in it, and happens to find a valid proof of work, and he happens to be first. So he finds this block and wants to publish it as soon as possible. So what happens then? Rashid's node will send to his peers a headers message. So this is Xi over here. So Rashid sends a headers message to Xi containing not the block ID, but the actual header. And he sends the header instead of the block ID for a good reason, because now Xi can check that the block actually, that the header actually fulfills the proof of work. She can verify the proof of work on the block header. If she would just get the block ID, she would need to request the header or the full block in order to verify the proof of work. And that would allow for someone to spam Xi with headers messages, with the transaction IDs. Sorry again. Someone would be able to spam Xi with block IDs, so that Xi would be required to request block headers or full blocks from peers. And that would eventually exhaust Xi's bandwidth, or at least degrade her performance. So therefore, it's useful to send the headers instead of the block IDs. Headers are 80 bytes long, so it's not a big deal. Block ID is 32 bytes long, but sending these 80 bytes is better because she can then verify immediately whether the block has enough proof of work or whether the block has valid proof of work. So it has valid proof of work, and she will request the block by its block ID to Rashid, and Rashid would reply with the block. She can request the block by its block ID because the block ID only depends on the header. It doesn't depend on anything else in the block, just the header. So she can calculate the block ID from there. Okay, so Rashid sends the blocks to his peers, and those peers will exchange headers between each other and blocks. So eventually, every full node will receive the blocks and verify the block. Sorry, so the recipient of the block will verify the block before sending it further. And eventually, every node will have this new block. And yep, so now we are going to look at how data is sent from Tom's node to John's wallet here, the sender, the original sender of this transaction. It goes the same way as between nodes at the beginning, at least. So Tom will send a headers message to John's wallet, and John's wallet will then reply. Since John is a lightweight wallet, it won't request the full block. It will request a so-called Merkle block. So it requests with a get data message, it requests a Merkle block with a certain block ID. And Tom will then reply with the header and the Merkle proofs for John's interesting transactions. And we talked about that before, how that works. And we won't go further into that. So this is how a lightweight wallet doesn't have to receive the whole block in order to get a single transaction. Yeah, okay. And John obviously verifies this inclusion proof, this Merkle proof, and verifies that the Merkle root is actually in the header and so on. And the same goes between the cafe's full node and the cafe's lightweight wallet here. So the cafe's lightweight wallet will also get a Merkle proof from the full node in the same way. And now we have fulfilled this cycle. We have gone from we created a transaction that propagated the peer-to-peer network and got propagated out to lightweight wallets, and also some miner picked up this transaction, put it in a block, and propagated the block across the full network. And also the lightweight wallets would get their Merkle proofs out to them so that they can inform their respective users that the transaction has been confirmed. So from now on, we will leave the silly cookie tokens and consider only Bitcoin from now on. So we have built the fully decentralized system that's censorship resistant. That's what we set out to do in the very beginning. We wanted to build a censorship resistant system, and that's what makes Bitcoin stand out from other systems. It's censorship resistance, and it's the first of its kind, and it's only of its kind. So I think this is a good time to take the break. So yes, let's continue where we left off. We have seen how both transactions and blocks can propagate the peer-to-peer network. And now the question is, how does a new node connect or start participating in this peer-to-peer network? So we're going to assume now that someone named Selma wants to set up her own full node in this network. And what steps are involved in doing that? These are 4 steps, but these are not all manual. Some of these are actually happening under the hood, but they are equally important for that matter. So we have 4 steps in setting up your own full node. The first step is to download and verify the integrity of the software and start Bitcoin Core. Bitcoin Core is some people call it a reference implementation, but it's the most widely used implementation of Bitcoin. So you should download Bitcoin Core and verify it with verify the integrity of the program. And the second step is to connect to some nodes in the network. And the third step is to download the blockchain from these nodes, from nodes, so that you catch up with the most recent block. And then you enter what we call normal mode of operation, which is the mode that we discussed on the previous half of this lecture. Okay, so we're gonna go through this. We'll start with step 1, obviously. When Bitcoin Core releases new software, when the development team behind Bitcoin Core releases new software, they create a binary and package it. Normally, if it's the Linux version, they package it in a file, a tar.gz file like this. So this is an old one, but it's Bitcoin 0.17.0 and so on. And here's the architecture, x86 64-bit, and it's for Linux and tar.gz. So they release this binary code here. And they also create a file that's called SHA-256sums.asc. And this contains signatures for a signature for this program, so that people can verify that the program is the one that Bitcoin Core intended to publish. So if you download the program from somewhere, anywhere, you can always make sure that the program is signed with a private key of Bitcoin Core, the Bitcoin Core binary release private key. So this file here, SHA-256sums, is created by the Bitcoin Core team. So they add a hash of the program here, and they add the program's name or the file name of the program, and they use that as a message to sign with their Bitcoin Core private key. And they put the signature in this file as well. So we call this the signature file from now on. And its name is usually or always SHA-256sums.asc. So when you download both Bitcoin Core and you download the signature file. But you also need this verification key, because they sign it with their private key here. And to verify this file, you would need the corresponding public key. And that public key is widely available. They publish it on bitcoin.org, and they publish it on bitcoincore.org. And it's also available on various sources. So when you have downloaded the Bitcoin Core file, or when Selma has downloaded the Bitcoin Core software and the signature file, and they have the public key, and they trust that this is the authentic public key. This is a pretty hard problem to actually know if this public key is the correct one. You have to ask several different sources to make sure. So you ask you look it up on bitcoincore.org's website, and you ask a trusted friend, or you ask on Twitter or anything to make sure. But once you're sure that this is in fact the public key, then you save this public key in a safe place, so that the next time they release new software, you don't have to go through that process of finding the correct public key. You already have it, so you can more easily verify following releases of Bitcoin Core. So you use this public key to verify this message, verify the signature, that this signature signs this message for this public key here. But that's not enough, because you have only verified the hash. You have only verified that the Bitcoin Core signing team, the Bitcoin Core team, has signed this hash only. You also need to verify that this hash is the same hash as the hash of the program itself. So you hash the tar.gz file, and you compare the hashes. If they compare, then you know that this signature is good for this program here. So now you have verified, or Selma has verified, that this signature is correct, and she can trust that this is the program that Bitcoin Core actually released. So she's not being scammed by anyone. And then she starts the program. Selma starts her program, which is Bitcoin Core. And it's time to find some peers to connect to. And this is also a hard problem. I mean, who do you trust? How do you find initial peers to connect to? There are several ways to do that. The most common ones are the one at the bottom and the one on the left. We'll start with this one on the left. No, we'll start with this one, hard-coded addresses. So Bitcoin Core comes shipped with a number, a list of hard-coded known IP numbers and ports. And this can be used by Selma to connect to existing nodes. But this is a pretty centralized way to do it. If the software would ship with if malicious actors would force the Bitcoin Core team to publish software that contains malicious nodes here, you would get in trouble. And the other way to get initial nodes is something called DNS seeds. And these are also hard-coded in Bitcoin Core. Bitcoin Core comes hard-coded with a number of names like this, dnsseed.bluemat.me. That's one of the DNS seeds. There are several. And Selma's node can use this to look up this name against the publicly available DNS server. DNS is domain name system. So it's the same system that's used to look up host names, look up IP numbers from host names when you browse the web, for example. But instead of replying with a single address, this DNS server will reply with a list of IP numbers that Selma can choose from. So And also each time this is requested, the DNS server will reply with a different set of IP numbers. I mean, I think they reply with 20 addresses on each request, but there are more addresses on the record under this name. So it will, I think, randomize the list of IP numbers there. So Selma will get initial nodes that way too, but most importantly, she can input her own nodes that she trusts or semi-trusts. She might have a friend that she will call and ask for her node addresses. So Selma asks she for her node address, and she will reply with this. And she can input this into her program and use that as a node as well. Okay, so that's how she finds initial peers to connect to. So that's just initial peers to connect to. The next step is that she will ask, okay, let's I was too fast there. So let's say that she wants to connect now to she's node here. What she does is that she sends a message. She connects to her IP number and port using TCP. And then she can send a message like this. She sends a so-called version message, which contains the protocol version and a string that's a software identification, but it can be anything. It's like if you know about the user agent in a web browser, it's the same thing here. It can be anything. And she also says that, hi, I'm at height 0 right now. And then she will reply back with a version message. And she has a different protocol version and a different software identification and a different height. And she will also immediately, after this message, just send a verac message, which is an acknowledgement. And Selma acknowledges this back. And since they have different protocol versions, they need to, this is a negotiation. Now they both know each other's versions, so they can use the version that both, so they will settle on version 70012. So this will be the effective version when they talk to each other. Okay, so now it's Selma has connected to Rashid and she, and she will now ask at least one of her peers for more peers, and Rashid will answer Selma with his peers or a selection of them. So Rashid will reply to Selma with a list of peers, IP number and addresses and ports. And then Selma will try to connect to some or all of them. So this is how she would, get to know the network. She has her initial immediate neighborhood, and from that she will expand her neighborhood by asking her immediate neighbors for more peers, so that she can have a decent amount of connections. You want probably quite a few connections in order to make sure that you are not being eclipsed, or so that you're sufficiently sure that no one is hiding influences, that information isn't being hidden from you. That's why you want many peers. And yeah, so this asking Rashid for more peers looks like this. Selma asks Rashid with a get adr message, and Rashid will reply with a list of addresses like this. What I didn't mention is that here, when you use DNS seed, the reply from the DNS seed request is just a list of IP numbers. You don't get the ports back here. So all these IP numbers are expected to run on the default port, which is 8333. Yeah, so now Selma expands her neighborhood by getting new addresses like this, so she can connect to those two. And now we are going to step 3, which is to synchronize the blockchain. And she starts by synchronizing just the chain of block headers. And that is a way for Selma to get to know where the most proof of work is, so that she's not fooled to get a fake chain that's not the strongest blockchain. So she asks Tom for headers like this. She sends a get headers message to Tom, and she also includes her own best header. And Tom will reply with headers that follow from this header. So this is the header of height 0, because Selma doesn't have any blocks yet. She only has the block 0, because block 0 is hard coded into the software. So everybody has block 0 from the get-go. And so she can send the header of block 0 to Tom, and Tom will reply back with a headers message with a list of 2,000 headers, starting from height 1 and 2 and so on. And Selma will take those headers, verify the proof of work in the headers, and when she's done with that, she has verified 2,000 headers. Then she will send a new get headers message with the latest. This is at height 2,000. This is the block ID of the 2,000 at height 2,000. And then Tom will reply with 2,000 new headers and so on until Selma receives a headers message containing less than 2,000 headers. Then she knows that there are no more headers to fetch from Tom. Okay, so now Selma has received all headers that are known to Tom. And then it's time for her to start requesting block data, because she has verified all the proof of work for the full header chain, and it's time to get the actual blocks for this chain. So she starts from block 0, asking for block at height 1, height 2, and height 3. So get data with 3 blocks here. And she asks Rashid for this. And Rashid will reply back with block messages containing the full blocks. And she doesn't have to ask for blocks from the same peer. So in this case, she asks Rashid for height 1, 2, and 3, and then she asks for 7, 8, 9. And that means that she asks someone else. Maybe she asks she for height 4, 5, and 6. So she can parallelize her download from multiple peers. Okay, so this is how she would download blocks one by one from multiple peers in parallel. And when she has done that, she will of course verify the blocks as they come in, and eventually she will be finished and she has caught up with the tip of the blockchain. And then she can enter normal mode of operation like this. And now she's a fully participating member of this peer-to-peer network. Okay, so this lecture was a bit easier than the last one, I think, and it's time to do some exercises. So you will do all exercises of chapter 8 except 8.7.